essa parte. E agora aqui não.
Mexe com tudo. Deve ser questão indizitomista, questão de singularidade lá.
É outra coisa, não me informa.
Sim, mas...
Espero que...
Deve ser essa forma quadrada. Além de trabalho, conhece o trabalho do cara lá que envolvido com Fabrício, com
históricamente. Yo me acuerdo de pequeño, los tres caballeros. E salía para ella.
Ainda era meia hora? O acidente chega assim.
Era de...
Como é que sabe o clima na hora? No tempo?
Então, tem três, né?
Vai falar amanhã.
Hoje,
A partir de que horas? Perto do chefe aqui. Clima tempo.
hoje tempestade,
a nossa demonstração assim, ó, se ela é zero, a gente perdia um pouquinho, então se a vida de zero, ele faz volta para
55% de chance.
agora, se soubesse que ela é zero, não tem caracterização.
Estar in the session of is the third and last talk about
Well, yesterday I stopped here. This is the end of the first part of the talk, where we put a theorem that proves the equivalence between between the integral characterization and the left one that I have now. And well, here I'm going to give some idea of the proof, just some idea. And remember number 9, that we have the theorem says that if we have this integral, the principal value of this integral equal to this expression for these three values, remember the side, etc. Well, here not yet. We have just an integral and three numbers with these conditions, these values of the parameters A. Then, under this condition, and if we suppose that y0 is positive and y1 is negative, then these two values, y1 will be the image of y0 by the left one that I have. This is what the theorem says. And moreover, it says that the flight time is this one. We were recovering the flight time and we obtained this expression, but now we have to use it to prove the theorem. And then, well, here I say, after some technical details about the flight time, what are these technical details? The flight time must be positive. And then we have to conclude that this is positive for all possible values of A. Two of them are trivial because A is positive, everything is positive. But if A is negative, then, well, we have to make a limit from y0 to infinity and y1 to less infinity, and then we are going to see that with this is less than this amount, so it works perfectly. The flight time also must be positive until we reach again the separation line. And well, in this, let me tell you that this expression is obtained from just was obtained from the left one can have up with different positions of the equilibrium. I must tell you that if we don't stop here, if we continue this curve and we intersect again, or we intersect again or again, imagine a focus for instance, then this number, this k, has to be from 0, 1, 2, 3, 4, 5. So this is more or less like an index function, This is important to avoid, this is something that Antonio Teruel asked me yesterday, and it is a good point, to avoid possible spurious solutions that you may have. If, for instance, if you take the solution, then intersect, and then y1 is this one of here, no? And you have an intersection in between, no? And to avoid these cases, these values doesn't allow you to go more than a half of a loop. Okay? So, well, and now what we have to do is to see that the point 0, y1 is exactly the same that the flow applied to the initial condition 0, y0, and with the flight time, or with this time that we give here. We must prove these two things, and then it is obvious that y1 will be the image of y0 by the left one cadena. And to do this, we use some things that we have seen in the previous slide. For instance, we have seen that for y1 and y0, we have this logarithm equal to this expression, which is the trace times what we are now saying that it is going to be the flight. And on the other hand, simply because phi is the inverse integrating factor, we have this value, the inverse integrating factor evaluated in the image of in flow with initial condition 0, y0, and flight time tau. This is equal to this amount. So both are the same, and this means that this and this have to be exactly the same. This means that this point, we don't know if they are the same, but we want to prove this. But these 2 points are in the same level curve of phi. This is important for the integral that I'm going to explain. Okay, we have this, and both points are at the same level. And now, what we have to do? Yeah, just the ideas. We are going to take the field G, remember the orthogonal field with flow, and also conservative. And we are going to integrate this field on this curve. This curve has the segment that goes from y1 to y0. Also, this is an orbit, that goes from y0 to the flow at the time tau that begins in this curve. So and then this segment that joins these 2 points. Well, it is not a segment. This is a curve. It is a little curve of B, so it will be a part of a hyperbola or ellipse or something. Iconic section. Okay. Well, then we can obtain trivially from here that this integral of this field here is 0. Why? Well, here it is 0. Here it is the value of this integral. If it is 0, then it means that G has to be 0 also. If it is not 0, then it means that you have an ellipse, and well, I think that I need to write this just to clarify it. Imagine that you have a case where you have an equilibrium inside. This means that this is a focus or a center, and then the level curves of V will be ellipses, maybe something like this, and with the equilibrium here. Okay, so if the integral is equal to 0, because it's the case k equal to 0, then you choose this second. But if the integral is the corresponding V equal to 2, then the equilibrium is inside, then you have to take this other second. In any case, you have the integral in the interior of this zone equal to the left, to the right hand side, and this is 0, and this is the integral. So the integral on the segment must be 0, because it doesn't add anything to the expression. So this integral 0, and the only thing that we are going to do now is to develop a little bit this integral. As we are on a level curve of the inverse integrating factor, then if you parameterize this curve, then you will have something like a mu, a function mu of s, the parameter s, which must be positive or negative, never 0 because it is a parameterization of a curve, times the orthogonal to the expression of V, the gradient of V, sorry, orthogonal to the gradient of V, which is the tangent vector of the curve. If you remember, this G is the orthogonal field, is a field orthogonal to the original one, this one from here, and if you remove the orthogonal, well, this is the scalar product to vectors. If you remove the orthogonal, the result is exactly the same, and it is exactly as you write f times the gradient of V. And the definition of an inverse integrating factor says that f times the scalar product with the gradient of V is equal to the divergence of f times V. This is the definition of the inverse integrating factor. So V and V disappear. The divergence of f is just t. So this is your integral. That is just something that cannot vanish. T equal to 0. Well, for t equal to 0, I have written here. T is different from 0. For t equal to 0, it's trivial. This is a trivial case. I have decided to speak because there are many of these cases. I have gone to the principal idea. So this will be, if this integral is 0, this means that S0 and S1 must be the same. That is, the beginning of the curve and the end of the curve must be the same. So this point is exactly this point from here, and then I have finished. This is the left one that I have left. Okay? So here we have now we have already proved that both things are exactly the same. So from now on, we will use this to solve some problems. Okay. Let me tell you that I have to finish this first part by writing. I think that the best versions that we have now of the theorems related to the integral characterizations, they appear, let me, there are a lot of pages, but they appear in this work, which is our third or fourth work, I don't remember. But from the beginning of our work to this other work, we were trying to solve some problems, and then we decided that it would be necessary to write all these questions that I have telling to you in a better way. And then in this paper you can find this description of where Poincaré have mapped in terms of the integral characterization and also the right Poincaré have mapped. And these are the two theorems that we use in all our papers about limit cycles. Okay, it is not necessary for you to read because what we say here is exactly what the inverse integral, the integral characterization is this equation. If you have the y0, then this will be the image by the left Poincaré have map and all the other properties. But I have stopped here because I want to remember you that, or to remind you that this is very important. That is, the left Poincaré have map is this is an orbit, this vector field. It is a solution of this equation, this differential equation. And why it is important? Because this is usually what we are going to use. Then this differential equation does not depend on these cases. It's equal for all the cases. And well, let me show you how it works with some applications. So, well, in the theorem for the right Poincaré have map, we could decide to take two different maps. This is y0, then this is y1, and, or let me say, better than this, y of y0. From now on, this will be the left Poincaré have map function. And well, the choice is this. We could take this as the Poincaré, right Poincaré have map, but we say to take the opposite. That is this expression that will be it is backwards to the flow, so we call this the backward Poincaré have map. Okay? And we say that this is y0, and from now on, if we want to find a limit cycle, the only thing that we have to do is that this minus d is equal to 0. This will be the closing equations. So, well, this finish here, and then I'm going to change the document, and I go to the applications.
That's a question. It seems to me that in some of the slides you said that for the right half map, the only thing to do in the expression is to change the sign of the k, putting k negative.
Yes.
0, -1, or -2. This is okay.
Well, yes, in this case. It depends on how you take the right Poincaré map. If it is backwards or forwards.
Yeah.
Okay.
No, but
It is just a change of variables. You change t to minus t, but it is an invariant of the system.
the expression for the time would be negative.
Yes, in this case it's backward. But we are going to, for us the time is not important. It's not usually important because we are going to work directly with these points. With the flight time disappear. Remember? Okay. Then application to limit cycles. And well, the first thing is not an application, a direct application to limit cycles. Well, we present the general system is this one. We have two zones, two linear zones separated by x1 equal to 0. In the separation line, we have set the usual Philipov convention for the trajectory of the system, and 1958. And we know, because we have done this just for a linear system, we know that we can translate this system to a generalized linear form. But in this case, you must assume that this product, the coefficients y1, 2 of both matrices must be different from 0 to make this change. And as you can see here, to obtain this, the first one can be obtained as the usual generalized inner form of the system that we have analyzed. And in this case, you make this change here, you must add this term here. Well, it is not symmetric. You can try to do it symmetric, but it is not symmetric. And the best idea is to left one as easier as you can, and then to put this term here. Not in the first application, in the second one, we will see exactly the effect of this P, but you can imagine, if B is equal to 0, then you will have sliding radius. But if B is equal to 0, then it is different to 0, then you will have sliding radius. Then the problem changes. Okay. Let me tell you that this is not the last exercise, but it is an exercise prove that this is a necessary condition for the system of limit cycles. Well, it is not difficult. The only thing that you have to do is to see the flow in the separation line. That is, I'm sorry. And to find an homeomorphism present in the separation line that transforms this system in these two systems. Okay, there are many homomorphisms. You can choose a lot, but I give you this hint. This is a good change that you can find, for instance, in this paper by Freire, Ponce, and Torres. It is not the only one. You can find. You can try with this, but I think that it is a good exercise to go from scratch. Take a linear change on both sides, and then to try to apply all the conditions, and you obtain your own version of this homeomorphism. And something important, something very important. Okay? I don't know why, but this happens. Sometimes when you are writing some papers, some expression change automatically. Don't know why. Don't know why. And then, for instance, this part of this expression may disappear. And it happens to us, yes. And well, it is a pity because it appears in 3 different papers. So, if you are reading our papers and you find AR equal to this thing, black term, you must add this expression. Everything is correct. Everything is valid, but you have to do this. And be careful because it appears in some of the main theorems. I'm sorry. I'm sorry, but it is something that we do sometimes to see if the readers are learning what we put there. Nothing, so not nobody has read it. Okay. We have versions, the first versions of papers, manuscripts, with this expression correct. I don't know why in some moment, perhaps a copy paste or something, they decide to disappear. I don't know. Okay. So let's go to the first example, the easiest one. The Lumchuas conjecture, that is a conjecture about the number of limit cycles that a continuous piecewise linear system can have. Well, in this case, this is the system, the linear system, but as you can see, we have B here, and then we have a lot of parameters that are equal because this system is continuous. Okay? This is the easiest thing, the easiest system that you can consider in these piecewise linear systems. The limit cycles, it is just because it is the first time I talk about limit cycle. A limit cycle in this context is, as you can see here, a closed orbit, non-trivial closed orbit, isolated from other ones. Okay, this is the definition. So it masses twice the separation length, because if you have linear system, you cannot have mini cycles on one side of the other. This is something that we know perfectly. Okay, then Lumcius conjectures that a continuous planar linear system with two zones separated by a straight line has at most one linear cycle. And moreover, if this limit exists, it is a practical reference, so it is hyperbolic. And well, this is the conjecture. It was proven in 1998 by Freire, Oliva and Torres in this paper, doing a case-by-case study. This we have a salad, we have a focus, we have considering all the different configurations given by the spectral matrices. This requires different reasonings for every case. That is, it is not the same to have the expression that you obtain when you integrate a focus than the expression that you obtain when you integrate a saddle. So there are different reasonings to obtain the same result. And well, flight time appears, so the analysis is not easy. It's not easy. Well, as I said the first day, the use of the integral characterization is able to give us a short proof of this same rule. And well, we proved this in this paper, which is called a new simple proof for Lumcius conjecture. It has, I don't remember, perhaps 6 pages or something more or less, and 2 of them are drawings. Because the reviewer says, please, some drawing. So we put several drawings, and then it is a little bit. But as you are going to see now, it's very easy. I'm going to go step by step. You will understand perfectly. So this is our system. In this case, we don't have T because the system is continuous. We have also this condition. This A is equal here and here, and the only different parameters are TL, PL, and TR, TR, depending on the side. Okay. As you see, there are always one condition like this to perform the change of variable. Okay, so the exercise, the last exercise. Prove that no limit cycle exists for TL here greater than 0. And the hint is Green theorem or read this paper. But it is very easy. But you have to use these Green theorems with an orthogonal fit. I don't remember the name, but it is one of the propositions of this paper. And well, in this case, prove that no linear cycle exists for A equal to 0 if the system is homogeneous. So if you have a periodic orbit, then you will have a continuum of periodic orbits. It is not a difficult exercise that you can solve without any problems. But this allows me to remove this case. From now on, we will consider TL times TR positive. And any different concept. And this is what we say. Okay, let's go now to the Poincare maps. It is exactly the term is actually equal to this in the blackboard. We have Y0 and then the left Poincare map, Y0 and the right Poincare map. Forward or backward. And from them we define the displacement function delta, which is YR minus YL. It is done in this way. Well, we could have written the opposite, but in this way, when we obtain the parameters that says if the limit cycle is stable or unstable, then it is the usual positive or negative sign. And negative will be stable, positive unstable. So, delta of a value y0 star is 0 if only if there is a periodic orbit. This is clear. If the periodic orbit is a limit cycle, then first y0 must be positive, strictly positive, and yr negative, because it could be the orbit. No? In other situation, it could be the orbit. So remove this case. And it is a hyperbolic Planck cycle if the derivative of delta is different from 0. Okay? And in this case, the limit cycle is attractive repelling, provided that the delta is negative or positive. I told you in 2 minutes. Okay, well, then, from now on, we are going to assume that there exists a limit cycle. Sorry, a value y0 star where the displacement function is 0, a value y1 star will correspond to, in this case, to the backward and the forward map of y0 star, and that there exists also a periodic orbit that causes, this what means that there is a periodic orbit that causes transversally this function. Okay. The first important thing, the sign of delta, of the first derivative of delta, is determined by the sign of a quadratic function at this point. Why? Because it is known that YL and YR are solutions of this system. Well, sorry about the notation. We decide to repeat a little bit the notation. We decide to call W to the value of T over 0 y0. Okay, so this is exactly the same polynomial we have here. We obtained it, you remember, because it appears in the intervals. Okay, so these two functions are solutions of these equations, and these functions must be positive for every interval between YL and YL of Y0 and Y0, and also the backward application that this is necessary for the interval to exist. And if you compute this derivative, you see that it can be written as a function of the product of two functions. One of them, which is different from 0, we have here y0, y0 minus y1, one is positive, the other is negative, so this is different from 0, y1, which is negative, different from 0, and this is different from 0. So this function doesn't vanish, and the sign is constant. And this times this function f, which is this one. Okay, so the sign of delta, of the derivative of delta, is determined by the sign of this function, which is this polynomial of degree 2. That is what we were saying here. Okay? So this is the first important thing. This is something that we always do when we have to deal with limit cycles. That is, if we assume that there exists a limit cycle or a periodic function, then on this, under this condition, the derivative is going to be given by a special curve. In this case, this curve is just a hyperbola. I'm going to tell you now. Okay? Sorry. Yes? This expression, okay, that is quadratic. It's very easy to see that this is an hyperbola. Okay, this function, I think that I am going to reproduce at least the geometric part of this proof. Okay, I want to talk now about this quadrant. This is y0, and Y1. This is the place where the one guy maps are going to exist. Okay? And then Y in the fourth quadrant, because Y0 is positive and Y1 is negative. And then we call Q to the fourth quadrant, and the curve gamma is a hyperbola, I have told you. And device, it is possible to see it, it's very easy, it's a hyperbola, it's not a complicated curve, that it will separate this quadrant into zones, something like this. Imagine like something like this. Maybe, perhaps, some of these regions will not exist, because there are two zones. One of them is R plus and the other one R minus, which are determined by the sign of F. So this is gamma, this is F equal to 0. Okay? This is the function F equal to 0, and then we have the sign of F equal to a value, positive or negative. This value A, L, this value from here, is A times TL, because TR, I remember that this and this have the opposite sign, so this have the sign of TL times A, times A. So this is the sign. And one of these two regions is always going to exist, which is R plus, because this function, when you put when you write, I can mark here, when you put here the origin, then you have this expression that it has they have the sign of A times TL. So the origin is always in R plus. So this is the origin, this will be R plus. Okay? And if it exists, this will be R minus. Okay, let me go a little bit more. If we prove that the periodic orbit that we are assuming that exists is located here, imagine that this is this point, the periodic orbit. Then the stability is determined for the value of this function here will be hyperbolic. The only places where the periodic orbits cannot be hyperbolic are here. I remind you that this corresponds to delta Riemann equal to 0 if you are on the periodic orbits. Okay? So this will be they exist the non-hyperbolic limit line cycles for periodic orbits, and here hyperbolic and hyperbolic. Stable or not, depending on the values of A, R, and T. And this is important, this implies the uniqueness of the limit cycle. Why? The limit cycles for a system like this must cross this line, so they have to be nested. So if you have one of the equilibrium that is stable, the next one cannot be stable. You need to have something unstable in between. Okay? But you can also have non-hyperbolic, but as I want to prove, the non-hyperbolic are not going to exist because they are not going to be in this place. So the proof will finish if we in some way prove that the periodic orbit must be in this region. Why? Because any periodic orbit should have to be in this region, so that they will be stable or unstable, but you cannot have here another point with the same stability. You need to pass to the other side to change the stability. Okay? And then, okay. The trivial case, when this is empty, then we don't have anything to prove. It's obvious. The only point we have to be there. But when it is not empty, then what we are going to do is to analyze how is the flow of each one of the two differential equations on this line. Why? Because we know that the left one-and-a-half map or the right one-and-a-half maps are orbits of these equations. So imagine that we prove that all the orbits will go in this direction for both fields. Then the left and right one-and-a-half map will have to go over there. They will have an intersection here or not, but they cannot come back here. Perhaps someone may imagine, but yes, but perhaps they intersect here before going to this path. No, we are going to prove that this is not possible. And we are going to prove also that this is what is going to happen. Let me see that I prove it. Well, both the graphs of those functions are contained in the fourth quadrant. This is trivial. If we have a periodic orbit, then it must be in the intersection of both curves. And there is something important here. The equilibrium must be in the set given by these two curves. Why? Because the system is continuous, and you have A different from 0. So this means that you have, in the origin, you have a tangency, and in one of the two sides you will have an invisible tangency, at least in one of them. If you have an invisible tangency, the corresponding one-and-a-half map, right or left, will begin in the origin. And we know that we have a curve, one of the two curves that begin here, something like this. Okay? Something like this. And as I told you, if we take the vector fields given by the differential equations and we analyze the orientation of on the curve, this is a simulation, a special case. I have decided here to put YR, the one that is in the origin, and this is the other one-and-a-half map. So what we are going to do, as I told you before, is to see that these both vector fields will cross all the orbits of this vector field will cross this curve, the gamma curve, in the same direction. Okay? This is done simply by analyzing this scalar product. Okay? For the left side is this expression, for the right side is this expression, and since this is positive and TR has the opposite sign to TL, this always has the sign of E times TL. So this means that both vector fields cross this curve in this direction. So if we have one of the one-and-a-half maps beginning here, then when it crosses this of the one-and-a-half maps, just imagine there is one. I said I put white R here and white over here in the middle. Perfect. If this one crosses in this direction, then it cannot come back. So it will be here. And this one will be here. Maybe that we'll have one intersection, but no more. No more, because they are nested in cycles. And there cannot be intersections in any other place. In any other, perhaps. No, and in this case, yes. No, they cannot be in any other place, because these always have to be beginning in this point. So we have proof, almost geometrically, with some computations, easy computations, that for now this is the stability, no? That the solution this periodic orbit, if it exists, must be here, so it must be unique. So we have a limit cycle, and it will be stable or unstable depending on the value of A and T. So we have time. We have proved the conjecture. Sorry. Some conclusions. This is just a resume of all the things that I have been writing here with a little bit better drawing. It is a real case. I don't remember what values, but it is a real case. So as you can see, it's very easy. It is very easy. And what is more important, these are exactly the same ideas that we apply to the rest of cases, of more complicated cases. So you have a question or something, or it's better that I can follow. For instance, how I'm going to pass from this to the more complicated case, the general case. But in between we have, between this paper about the Lucho's conjecture and the last one about the general case, we have studied the Selwyn case. That is when all the orbit cross the separation line. The reasoning is the same, but when you have to study the behavior of the Poincare maps, the graphs of the Poincare maps, with respect to this function gamma when the derivative is 0, then it is not so easy. So you have to add some other important questions here. For instance, in this case, in the Selwyn case, we have to analyze what happens in infinity or in the origin, in the case that they are monodromic points. So we have several cases where or the behavior is this one, or the behavior is a little bit more complicated, and then to prove that there is just one solution, we must see that if you have two, then the second one will have a stability that it is the same that of the infinity or the origin, so it cannot exist. This is basically the kind of course. And always the same, but of course the expressions are more and more complicated. Okay? Tell me.
Just a comment. This idea that the same idea implies almost directly in the same case at most two. Then to take off, to subtract one off.
Yes.
Get one.
Oh, yes. I think that it is what I have explained.
Okay, no,
but sorry, no, it's not by you, it's by me, because I have explained this and I have said, sorry. Yes, thank you. So, well, this is a theorem that is necessary. You want to read it, and you have the paper, and perfect. You can write it in the paper, and you will see it. It is very short, and the ideas are these ones. I think that I have not forget any details. So, this is the reason. That is upper bound. I'm going to talk now about the generic case. That is the case. Well, this is a little introduction, talking about the Hilbert-System problem, because well, I think that it is important to say that it is very difficult to find upper bound of this problem. You know, the problem, the second part of the problem is talking about the amount of limit cycles that polynomial systems may have, depending on the degrees. And for h equal to 1 is trivial that there are no limit cycles because they are linear systems, and for 2 it's not so. So for 3, 4, you cannot say almost anything. But you can say a lot of things, but not the bound, which is the problem. So if you get an upper bound of something, I think that it's a good thing. Then we have done this for this system. For the system that now it is the general system again. It's a Iceland linear system. This is an extension of the the Hilbert problem. It's not the real Hilbert problem because these are algebra linear systems. But now I have just tell you that, for instance, for the continuous case, we have at most one. I also tell you that, and this is proved by us, that without sliding or escaping radius, that is just crossing curves. At most you can find one, and several years ago in 2012, there were two works in the same year where Wang and Yang numerically proved that there exist 3 limit cycles in one of these generic algebra linear systems, and also put this result, but in this case theoretically, that there are 3 real limit cycles in this system. And well, as I have said here, at this moment we don't know if there are results about upper bounds in the generic case, and we have this theorem that says that there exists a natural number less than 8. This is because the number we have is 8. We think that it can be less than 8, but well, we have obtained 8. There is a natural number 8 that any kind of algebra linear system have not more than L-star limit cycles. And now I am going to tell you the ideas of them. This is a little bit more complicated. We need to use more complicated theorems also. Well, let me tell you the principal ideas, not the details in this case. So, the first thing, write the system in its generalized linear form with this B here. I have here put a drawing of a sample of flow, but we have here a focus, and I think that here we have a saddle or something like that. That is just to make an illustrative drawing of what we have. For B different from 0, then we have here this zone where vectors point in opposite directions. You know that this can be sliding or escaping radius. The forward Poincare map, the left one, can be defined as usual. The right Poincare map can be defined as usual, but we have to see here that this B, let me show you. Okay, if you have the left Poincare map and the right Poincare map, the forward Poincare maps, this is the displacement function. Okay, and this is the important thing. If you have the backward Poincare map for this part, for a value B, then it can be written just with this translation. It can be written as in terms of the backward Poincare map for the case B equal to 0. And this is the one we control very well. This is the one we have in the theorems. The only thing we have to do is make this small change. From now on, I remove this 0 from here, and this is the function that we are going to study. This is the delta. Okay? So, the delta, I remember you, was this curve here. Now, we take again the vector field, and remember that both Poincare maps are solutions of these differential equations, these two differential equations, and this is important because they are solutions of these differential equations or cubic vector fields. They are not polynomial functions, but in some way they can be used. And now we are going to see this as polynomial functions. That is, the problems of intersections between these curves will can be written in terms of polynomial systems. Okay. Well, then we take the displacement function. We assume that if you move the the right backward half map up or down, then maybe the intervals where they are defined have an empty intersection. So in this case, there are no periodic orbits, there are no limit cycles. So forget this case. We are going to assume that they intersect, and it is not the empty set. So, okay, something important is that the simple zeros of these displacement functions are transversal intersections between the graphs of the two Poincare half maps, and they are also hyperbolic limit cycles of the system. So we are looking for this transversal intersection. And now, let me tell you a little bit about this. These are just the ideas, so I have removed a lot of quotations, and I say here, as a direct application of a technical lemma for analytic function, this is a lemma that we have in the paper that tells you that if you have, let me make just a little bit that way. Imagine that you have a function with two variables, analytic function, and then you find a zero, which is not simple. Imagine this one is not simple. Then, depending on when the derivative is not simple, the first derivative will be zero, perhaps the second zero or not, or the third zero or not. So depending which is the degree of the derivative, which is zero, then you will have one or another behavior. This another number that you will have, imagine that this is a parameter. Parameter I want to be big because it's the one that we use in our. If the derivative is zero until every value of the derivative, and then it is not zero, then what is going to happen is that when you move a little bit the parameter, if this is the derivative with respect of this parameter of this function in some way is different from zero, then you will have something like this, function like this. But you can also have something like this. In any case, that is, you will have something like a fold bifurcation. In any case, these are, let me put this in another place. Imagine that you have simple and non-simple zeros. In any case, at the end, the number of, sorry, simple and simple, yes, sorry. If you have a bound for the simple zeros, then you will have also a bound for the non-simple zeros. This means that we just have to look for hyperbolic solutions. We just have to look for these transversal intersections. Because if we have a bound for them, then we will have also a bound for these limit cases. Okay, this is the lemma, the technical lemma. And then this means that from now on we just have to study limit cycle, hyperbolic limit cycle. And the bound that we got often is for hyperbolic limit cycles. And then we do exactly the same as before. Now we take the derivative of delta. In this case we obtain a function f. In this case it's a little bit more complicated. It's degree 4 in the Lumchua's conjecture in the continuous case, and the degree was 2. And well, the expressions are more and more complicated. And as you know, this curve will separate the positive and the negative, the stable and unstable hyperbolic limit cycles. And something what is important is that, well, something that I said here before. Oh, I have the drawing here. I'm going to put the show there. Yes. If this is f equal to 0, and you want to have two hyperbolic limit cycles, then you have to close this curve. YL, YR should close this curve because you cannot have two consecutive limit cycles together. So each time that you close this line, then you can have another more limit cycle. Imagine that you have two intersections between this curve and this, and then you will have 2 plus 1 equilibrium. Possible intersections and possible limit cycles. Okay? Since both curves must cross this line, we are going to simplify a little bit this problem. We take one of them. For instance, YL. And then we are going to see how many intersections YL this could have. Okay. If we have 8 intersections, then at most there will be at most 9 possible limit cycles. And this is one of the bad things of our method. That is, we are obtaining an upper bound. And we must always see in the worst possible case. That is, perhaps this intersects 3 times here, but there are only 1 intersection. But we cannot control this. So if we have 3 gaps here, then we have to say that perhaps they will exceed 4. And then this is why we are not obtaining the best possible bound, just 1 upper bound. So, well, this is what I have said. Now we are going to see the intersection between YL and F. And it's F equal to 0. Okay. This is also important. Now we use an extension of a theorem by Khovansky. Khovansky, 3 minutes. I finish. Yes, very fast. Khovansky analyzed eunomials. It is very related to what Armengol was telling the other day. The number of zeros, of real zeros, polynomials, depend more on the number of monomials than on the degree of the polynomials. And he also has a lot of results about intersections of algebraic curves and non-algebraic curves that correspond to a vector field, which is polynomial. And so we have to change a little bit one of the results by Khovansky, because he works in the complete plane and we work just in the 4th quadrant, or even less, depending on the intervals where the functions are defined. And we reproduce this theorem just for connected components. So what we have to do now? Well, the theorem says that the number of isolated intersections of YR and F equal to 0 is bounded by the number of connected components of F equal to 0 and plus the number of contact points between F and the vector field XL. And finally, you make all these things, and you will have awful polynomials. But if you reduce the degree, if you look for solutions inside or outside of our region, you can see that most you can have 5 points, 2 connected components of F. This is 7 plus the number of intersections plus 1 possible limit cycle. So again, we obtain this 8 that it is here. Okay, so this is the idea, no? And then to finish, there is still much more to do what we thought. And this point also. Okay? We now, for instance, let me say this, following an idea by Armengol, we were always worried about the common case, to study everything for all the cases at the same time, because this was the origin of our theory. But he told us, perhaps this theory can also be applied to particular cases. So something that we have done is to apply these same ideas to the system of Wang and Yang, the system of Torregrossa, Freire, Torres, and Ponce, which has three equilibria that comes from infinity, and also work by Gabriel, Armengol, Paulo, about the holomorphic linear systems. And in all of these cases, we have been able to prove that most three. So we have the proof that all these systems have exactly three limits. And then, well, this is all I want to tell you in this course. So,
It's time for questions and remarks.
I have another problem for you. Yes, you know about the Koppel question. Koppel problem is harder than Hilbert problem. Koppel says, determine the exact number in terms of the parameters. This is Koppel problem. But I wonder if in the case of Schur's conjecture, can you characterize there exists limit cycle if and only if? Because we not at most one.
not a number one. To say,
If and only if. And this is also very interesting from point of view. So maybe in this case the course is prepared, but maybe, who knows?
Douglas, it's another problem. Now we are doing what Armengol says.
In the case of generic linear homomorphic systems, not particular systems, but true linear homomorphic systems, the upper bound is still 8. It is not.
Yes, this is for all generic linear systems.
Perhaps it can be improved.
Yes, if you restrict to homomorphic systems, maybe
we have not studied
it's less than 8.
this case.
It can be improved to 7 at least,
Oh, I see.
because it's
Yeah, but the problem is that the equations are very complicated. And it is very difficult to time bounds when you have parameters. When you have a particular case, then it is easier, of course. We don't know, but it's another good question.
One more question. The next speaker is Professor Francis Mortier.
Exatamente, é um absurdo.
The next speaker is Professor Francis
Posso
Mortier.
passar, desculpa.
He will talk about systematic study of two-layer canal cycles. Okay?
So let me also thank the organizers for inviting me. Really glad to be here. So as I thought, this is a joint work with Peter Damasco, Karel Bergers. Let me first, before starting, repeat a number of definitions. There might be people in the room who were not really acquainted with this subject. So what is for us a slow, fast familiar vector field? Well, I will restrict here to, let's say, the plane with you have a singular parameter epsilon. And a slow fast family of vector field is a smooth family. Everything's infinite. X epsilon lambda, a lot of parameters lambda. And you can write it as, let's say, a vector field which, let's say, has a curve, but it is regular. So this, this is a vector field with a curve of singularities. And to be more precise, it can be written as a function times a non-zero vector field. And so Z lambda is a vector field without singularities, and F lambda is a function with a regular set of zeros. So we do not take, let's say, algebraic varieties or whatever. Then you have a first order perturbation, and then you have all the rest. For those who are more acquainted, if you have this locally on a manifold, then this is called an admissible chart, but there's no need to think about working on a manifold. There is enough to see on a plane. There is an intrinsic definition of what is the slow vector field. So you have here the zero set of zeros for x 0 lambda. You have the tangent space. This is the fast foliation that is given by that vector field Z, because it has, of course, it defines what is called the fast foliation. And then you project Q lambda, so the first order perturbation, you project it along the fast leaves onto the tangent. And that is the intrinsic definition of slow movement. I repeat a number of notions which are not unimportant. There are in fact two kinds of layers. And what is a layer? That is, we talk about a layer of fast orbits. Here also you have a layer of fast orbits. And there is in fact a big difference, as we will see, in between what we call now a terminal layer. You enter the layer and you go back. And a dodging layer. You enter it, you do like crossing the street and you continue. That's a dodging layer, that's a terminal layer. And that's the kind of things we are going to look at. This is a transitory case. We do not look at transitory cases. This is a common slow fast cycle. We do not look at common ones. We admit two braking mechanisms. A Hopf braking mechanism and a jump. By braking mechanism, I mean that there is here a connection in between two jumps, but there is a way of breaking it in a regular way. It can be like that too. How do we study, how do we look for limit cycles across orbits? We take somewhere a reference here and follow it, and it becomes a reference center manifold. And then from here on, we follow all the rest. And you see then you always stay on one side of the reference chosen. Here, you must always take the reference far enough so that what you want to study remains on one side of the reference. Of course, we could also come from this side. You had already the braking parameter B in the jump case. This was clear. In the Hopf case, this is where is it? In the Hopf case, this is a normal form up to equivalence for Hopf braking mechanism. It is a singularity that moves along the curve, the critical curve, but that is not what we call a braking parameter. In the Hopf case, you divide A by square root of epsilon, and that's what we call a braking parameter. The reason is simple. In order to study what happens in a Hopf bifurcation, you blow up. And once you blow up, you really have a breaking of center manifolds. Because here is a center manifold on the blown up locus, here is another one, and they break, and that is related to A divided by square root of epsilon, so we call that a braking parameter. we do not need to go directly from a layer to, let's say, from a layer to the target. Target is always in the braking mechanism. You can, in between, jump as many times as you like. Sometimes people like to jump. So you have here a regular jump, another regular jump, another regular jump. In between does not matter. You can also have what is called, this is called an attracting sequence. You can also have a repelling sequence. It's the opposite of an attracting sequence. And then what do? In order, what you need is a good description of the mapping that goes from the layer to the target. That's what you need. And if you really, we got a good description, as you will see, quite strong. And in order to get that description, we use lower center manifolds. We prove that all the center manifolds that you encounter in this kind of problems are smooth. We use smooth normal forms. We use smooth functional admissible monomials. I'm going to say in a moment what I mean. And it takes about 170 pages, and then you get a good description of such a mapping. The last notion that I need is the notion of slow divergence integral. So you take your critical curve minus the contact points, and then take any parameterization. I give here not the intrinsic definition. There exists an intrinsic definition, but let me do it using a parameter. So you use whatever parameter you like, call it R. Then you can write in this parameter your slow vector field as q lambda r delta r. Related to this is a differential equation. dr ds is q lambda r, and so you define the slow time. So in fact, the slow time is defined wherever q lambda is non-zero. So it's outside the zeros of the slow vector field. And then the last notion you need is the trace of the differential of x0 lambda in the points of the critical curve. And when you then integrate over a piece gamma lambda, let's say that trace using the slow time, that's what is called the slow divergence integral. People used to call it divergence. In fact, you do not need a volume form in order to define it, but if you have a volume form, it is, of course, the divergence. And this was the last notion that you need in order to give this expression. Structure of the transition map starting at a layer section going to the target section in the jump case can be written as, and this comes from the reference center manifold. So it is, the A just stands for attracting sequence. It can be as long as you like. So you have a smooth function depending on the parameters lambda. Here you have epsilon to the power 2/3, another smooth function depending on lambda and epsilon. And here I say something wrong. It is not a smooth function depending on lambda and epsilon. It is a smooth function depending on epsilon to the power 1/3, epsilon to the power 1/3 ln epsilon, and then lambda. And these are in this problem, admissible monomials. But at least the mapping is smooth, but smooth in these variables. The same here, then you have a plus or minus 1, depending on the orientation you choose on the target curve, or on target section, and exponential. And here you have the slow divergence integral. Here we let it depend on u, so we choose u as a variable on the layer section, plus a big O of epsilon to the power 1/3, all this divided by epsilon. And again, this big O is a smooth in u, epsilon to the power 1/3, epsilon to the power 1/3 ln epsilon, and lambda. And in the Hopf case, it is exactly the same thing, or almost the same thing, except that you do it after blow up. You have something smooth in lambda, epsilon to the power 1/2, a function that is smooth inadmissible monomials. The admissible monomials this time are u to the power 1/2 epsilon 1/3, epsilon 1/3 and an epsilon lambda, plus or minus 1, and here again an expression that is completely similar. So that's the expression that we are going to work with in order to find limit cycles, right? So people who already know the Hopf bifurcation, let's say the Hopf breaking mechanism, might ask, what is that strange epsilon 1/3 doing there? Because that you do not find in Hopf. But it is, I say, after or before Hopf, you have an attracting sequence. So you can have a lot of jumps. And it is exactly those jumps that give rise to these epsilon to the power 1/3. So this is the general expression that we are going to work with. So now, when you come from one layer, and you have something else coming from another layer, then in order to see where do they come together, what you need to study is something like that. You have a function lambda epsilon plus e to the power ia u1 lambda, etc., minus theta c e r bar. I put a bar over the r because we do not really work with the repelling sequence, we work with the opposite of the repelling sequence. Always work with things that are negative. But now this theta c, you do not have a choice. Instead, this plus or minus, but it depends on the geometry, it is intrinsic. Because either you are both on the same side and you need to use plus, either you are on two sides and you need to use minus. So this theta c is intrinsic in the problem. And you can always take alpha in a way that when you consider it at d mu 0, epsilon equal to 0, it is exactly equal to the breaking parameters. So that's what I explained. If you have theta c as plus 1, we call it side preserving connection. And if you have theta c as minus 1, we call it the side reversing connection. And in the calculations, it's quite important. But you might ask, how are we going to do this? If you look in the book, it takes pages of pages in order to show what you need to do in order to have the exact theta c. In fact, it's very simple. You choose an orientation along the Canard cycle. For instance, you take 1001 as positive and represent it counterclockwise. And then you check whether the passages from slow to fast when you enter a layer, and those from fast to slow when you leave a layer, are positive or negative. And you do not need to mind about the intermediate steps in the attracting and repelling sequences. And then you will see that the connection between two pluses or between two minuses is side preserving, a connection between plus and minus or minus plus is side reversing. Example. This cycle, we call it the dp-dp cycle. So you have here dodging, another dodging. And if you look at the signs, you turn this way, that's negative. Here you turn this way, that's negative. Then you turn that way, that's positive. And you turn that way, that's positive. So here you go from negative to negative. So you may be sure the connection is side preserving. Here you go from plus to plus, the connection is side preserving. So that's quite simple. In fact, this dp cycle, Robert Rossari and me, we studied it about 20 years ago, but we only studied it for Liénard equations at that time. In the meantime, you see that you can have a lot of attracting sequences, etc., repelling sequences, but we now know much more, and that's what I'm going to talk about today. So what did we prove about 20 years ago? It has been published in 2007. That is called this integral I, slow divergence integral. And that one J, so attracting in this direction. This one K, and that one L. It's important, and constantly in this talk going to work with I, J, K, L. And that was the theorem that we had at the time. So, if you take the total slow divergence integral of the two-layer canard, you see that you have I minus j plus L minus k. So, the total slow divergence integral is I minus j plus L minus k. And the results are the following. If this is non-zero, then a hyperbolic relaxation oscillation bifurcates from the canard cycle under consideration. If D is zero and I minus j, that's the two in top there, the difference is non-zero, then a codimension 1 semi-stable relaxation oscillation bifurcates from the canard cycle, and this semi-stable cycle is generically unfolded by the parameter. Here in the notation is still breaking. This in fact, okay, you can work with a theorem, but in general, for the rest of the talk, we will work with two breaking parameters. But it was cited that way. AB for epsilon strictly bigger than zero small enough, producing a pair of hyperbolic limit cycles. And then the last was if D is equal to zero, I minus j is also equal to zero for a certain choice of two-parameter canard cycle, and if moreover the curves I minus j and L minus k cut transversally, that's that condition, then a codimension 2 relaxation oscillation bifurcation from gamma mu0 v0. The limit cycle is generically unfolded by the parameters, and producing systems having 3 hyperbolic limit cycles. Right. So this theorem, we in the beginning only proved it in a specific case in linear equations. And then, as we will see, there are other types of two-layer canard cycles. And the question is, do you still have that theorem in the other cases? And the answer is no. And that's what I'm going to talk about now. What do you need to do in order to have an overview of what you need to calculate? We introduced, in order to study n-layer canard cycles, we introduced the connection diagram. What is the connection diagram? Well, you take a circle, connection 1, connection 2, 3, 4, 27 if you have a 27-layer canard cycle. And then you put the signs where you enter, where you come out of a layer, let's say, where you go towards the connection, here when you go away from the connection, etc. So you add these signs. And once that you have done this, you see a lot of things. Here you go from minus to minus. That's necessarily in between a terminal layer. You go from minus to plus, that's a dodging layer. Here again a dodging, and here terminal. Here you go from plus to minus, that's time, that's side reversing. That's side preserving. Side preserving, side reversing. So on the connection diagram you see everything. And yeah, it's much simpler than, let us say, looking at the canard cycle itself. Here all the connection diagrams with 2 layers. So I start with a plus everywhere and then all the possibilities. What do we get? You see that this here, plus, 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 that's TP, TP. So terminal, preserving, terminal, preserving. Here you have DP, DP, DR, DR, TR, TR, and all those are DR, TP. So there are 5 possibilities. Of course, pay attention, we have here one connection diagram, but it can be represented, it can be found in an infinity of possibilities. Because you need 2 layers, but you can add how many jumps as you like. Here are examples in linear equations. That's in a classical linear, you can have a dr-dr cycle. See, dodging, and here you see from minus to plus it's reversing, from minus to plus it's reversing. So this is an example of a dr-dr. And you will see that the results on the dr-dr are different than the results on the dp-dp. This is an example of a DPTR cycle. You will not find an example on a classical DNR. So you need a more generalized DNR in order to find one. But you see dodging, terminal. And here you have a repelling sequence. You need it. That's an example with two terminals. So, terminal, terminal. Here everything is plus, so it is TP that you have, right? And then the last example, TR-TR. Again, NENR, but this is about the simplest example I found. So here two hops, and you see again terminal, terminal, plus plus, minus minus. So here you go from plus to minus, so it is TR-TR. So terminal reversing, terminal reversing. These are the 5 possibilities. You have them in linear equations. And there's no room for limit cycles. How do we do this? So like always, here the first connection, here the second one. This I call I, this I call J, but in this direction. This is L, and let's say this is L, and this is K. This is K in this direction. So here we start with the coordinate U on that layer and V on that layer, right? So what do we need to solve in order to find the limit cycles? First, some remarks on the signs of the derivatives, because they are important. We can always choose the orientation of the section sigma L and sigma R. That is the section that you have here. Think about the canard cycle. And we can always take the orientation in a way to have that the derivative of I with respect to U is strictly positive, and the derivative of J with respect to V is strictly positive. The signs of the other derivatives are then determined by the type of the two layers. In a dodging layer, you will then necessarily have that this derivative is negative, implying that the derivative of the total divergence inside that layer is strictly positive. Makes a dodging layer much easier than a terminal layer. For a terminal layer, okay, these signs are opposite. Okay, and now that's the kind of system that you need to solve. If you want to find limit cycles, then you look at the following. You have an exponential of a certain function I tilde U epsilon theta divided by epsilon, minus a theta 1, which is plus or minus, depending on the connection diagram, x j tilde, minus b1 is the first breaking parameter, minus a function epsilon eta equal to 0, and the second is x L tilde v epsilon eta divided by epsilon minus theta 2, x k tilde minus b2 minus phi 2 equals 0. Okay, so that means that you have to solve a system in which you have a lot of exponentials. That of course tend to 0, in the limit there is nothing. It tends to 0 when epsilon goes to 0. And these functions I tilde, j tilde, L tilde, k tilde, and the function phi 1, phi 2 are smooth in U, eta, epsilon 1/2, epsilon 1 over 3, epsilon 1 over 3, and an epsilon. And the functions phi 1, phi 2 are of order O epsilon 1. It's important, if you start deriving, for instance, with respect to B, then this it will give something extremely small, this will be O epsilon 1, and this is going to be something which is quite nice. And these functions are very close to the divergence integrals. Because for epsilon equal to 0, they are equal to the divergence integrals. So what you need to solve is this system here. F of U, V, B, mu epsilon equal to 0. And F is smooth. Up to now in all our papers, also in that paper that we solved 20 years ago, we could not use the smoothness because we didn't have it. So we had to do it a little bit in another way that was sometimes a little tricky. But now we have the smoothness, of course, in admissible monomials, but you can very easily work with it. So as I already observed, the partial differential dBf is invertible for small epsilon if we keep b close to 0 and mu in some compact. So you can use the implicit function theorem. So what are you going to find? You will find a family of mappings from u, v, let's say, okay, I should have uv here, from uv to b. So b is equal to b1, b2 is equal to phi epsilon u1 v, uv, satisfying, here it is written in correct way, f of u, v, phi epsilon mu, uv, mu epsilon equal to 0. And all these mappings are smooth. Also, that mapping is smooth in admissible monomials. So from now on, I'm going to forget about the extra parameters, the mu. I will restrict my parameters to the breaking parameters. And already see what happens when you only have breaking parameters, right? So the system of equations defines a map from uv plane to the b1, b2 plane. And for epsilon strictly bigger than 0, the counter images of b1, b2 correspond to limit cycles. Okay. So wherever phi epsilon is invertible, you have one counter image. So if you want to find the places where the bifurcations of phi happen, then what you need to look at is, of course, the determinant of d phi epsilon uv. So to find the singularities of phi epsilon, for epsilon strictly bigger than 0 but small, we consider d phi epsilon and calculate that determinant. Now, in fact, working with that determinant, except at the end, reveals not to be very pleasant. But there is your implicit differentiation. D phi epsilon is seen to be some regular linear mapping times the UVF. And the UVF is much simpler to work with. So of course the determinant of this mapping will be 0, if and only the determinant of this mapping is 0. Okay, and that mapping in the two-dimensional case looks like this. I mean, the two-layer case looks like this. But if you see it in an n-layer problem, you have an enormous amount of zeros. It's a really sparse matrix, easy to work with. So here you have a derivative with respect to u. That is I tilde prime. That's with respect to u. K also derivatives with respect to u. Here derivatives with respect to v. And here derivative with respect to v. And now we need to calculate the determinant of this matrix. So, back these epsilons just multiply by epsilon square. Epsilon square delta bar uv epsilon is just calculated and you get this expression. It still looks awful to work with. So we make it a little simpler. We put here I prime, L prime. Then here we take these exponentials. And if you do it that way, then you get here x of d tilde being the perturbation of the total divergence integral minus this here. This is non-zero, so the zeros are here. So we need to work with this. So we get delta bar is 0, and hence delta is 0, if and only if x of d tilde over epsilon minus this here is equal to 0. And then, so this d tilde, I already said, is a perturbation of the total slow divergence. So that's not so bad. But then let us look at this here. I write it in a different way, but I forgot my primes. So here nothing spectacular happens. The primes were forgotten, that's all. But if you write it this way, then you see this is strictly positive, this is strictly positive. Here, the number of negative signs, or the number of -1, is the same as the number of touching layers. And here, the number of minus signs is the number of side reversing connections. But think about your connection diagram. You start with a plus, and you end up with a plus. So the number of switches from plus to minus is even. So that means that this is always strictly positive. Since it's always strictly positive, you can take the logarithm. So that means that this equation here, you take this equal that, you take the logarithm on both sides, and you finally have d tilde minus epsilon log this equals 0, which can be written as duv, that's a total slow divergence integral, plus O epsilon 1 type of perturbation, and everything is smooth in these admissible monomials. But at Canard cycles, where the total slow divergence is different from 0, we already know that Hausdorff closed in the Canard cycle there can be at most one limit cycle, and it is necessarily hyperbolic. This was proved in that paper, but now thanks to the breaking parameters and the map we get, we know that as long as P is in the image, there is a limit cycle, which is hyperbolic. So that's P. Okay, then we need to look at Canard cycles where the determinant is 0. And there we can rely on the theory of singularities of maps from the plane to the plane. So here, we call this S, just where the determinant is 0. And what do we need to look at in order to see what kind of singularities do you have? Well, first, we have learned in the talk of Mike Jeffries, you can do it by using your B and G calculations. You will find what you have. Here I will do it in a more geometric way, like it has been done by Whitney, for instance. And what will happen is that you need to look at S, the tangent planes of the tangent lines to S, but also to look at the kernel of that mapping. So you need to look at the kernel of E phi epsilon. And then you need to look at the relative position and what happens between the kernel and the tangent line. But the kernel is very simple. It is one-dimensional, and it is this here. V is theta 1, I tilde prime over j tilde prime x I tilde minus j tilde over epsilon nu. You can also write it with respect to k and l, but let us stick to this here. And then you see that here something, okay, there are a lot of people here in the room who like discontinuous fields. Well, you will be happy, because this here, let us look what happens. If I minus j is strictly positive, then this tends to infinity. So this tends to the vertical position, right? If I minus j is negative, this tends to 0 for epsilon, so this tends to horizontal position. So what happens when what happens when I minus j is 0? That is continuity, right? Okay. We will try in this talk to avoid the discontinuity. So we will tackle the discontinuity later on. It's a work in progress. We hope so. And that's how S looks like. Yeah, this S looks like this. But we need a generic condition. We need that this can be 0, all right. This can be 0, but never at the same time. We do not yet accept it because it is still too difficult to treat it. So under this generic condition, we necessarily have that S is a regular curve. But if you take the touching cases, that means that this is non-zero, that is non-zero, then necessarily it is a graph from U to V. So quite simple. If you look at the dodging terminal case, then 1 is for sure non-zero, and well, effect we will always take in this talk that non-zero. If you look at the dodging terminal, then you still have a graph, but this time the graph can have minima, maxima, it can have, let's say, critical points. But if you look to the cases terminal-terminal, then it's no longer a graph. It is some curve, and you have segments going from the boundary to the boundary, etc. And you might have closed curves too. So it is starting getting complicated. So already a first result, generalizing the result that we have. If I minus j is different from 0, if this derivative is non-zero and that derivative is non-zero, then you necessarily have a saddle node bifurcation of limit cycles. And you can even generalize this a little bit. Assume that I minus j is strictly positive and that the tangent is not vertical. Because what you always need in order to have a saddle node is that your kernel is transverse to your tangent. That's all. So as long as, let's say, 1 tends to infinity, but your tangent is not vertical, you get transversality, so you have a fold, you have a saddle node bifurcation of limit cycles, etc. The same on the opposite. And so what we need in certain sense, I'm not going to say to avoid, but what are the interesting points that might give you cusps instead of faults? You call a point a kernel singularity if I is equal to j, or equivalently k is equal to l. And then you say that the kernel singularity, so that's one of these cases where you have that discontinuity. Yeah? So the only thing you must see is that at the same time, your tangent is not horizontal or vertical. So in order to have transversality. So you take this, you suppose that the curve I minus j equals 0 cuts k minus l equals 0 transversally, and you ask that both are non-zero, both derivatives, so as I told you. Then you have the following proposition. If a certain quantity is strictly positive, but what is this quantity? If you think about the first case that we treated, this was strictly positive, this was strictly positive, but this was strictly positive, so it was strictly positive. We only had that case. And we could prove, of course, there exists a unique function, u0 epsilon of class, say, infinite epsilon, such that the point u0 epsilon v0 epsilon is a cusp singularity. And for all u sufficiently close to the point, let's say you have the point, you have a fold singularity. So this is, there is a cusp. And this is what you call an active kernel singularity. But if you do not have this condition, if you have the opposite, then we call it a mute kernel singularity. And that makes already a difference, because if you go to the VR case, you can have mute singularities. So although you have the same conditions as before, you do not guarantee to have 3 limit cycles. On the contrary, you only have 2. Another interesting case is the tangential singularity. A point u0 v0 is said to be a horizontal tangential singularity if this derivative is 0. And you do not want to take it to degenerate, so you ask the second derivative non-zero. That's one of your G conditions. If you just calculate it, you will find the same results, of course. Yes, a point u0 v0 is said to be a vertical tangential singularity, j prime minus l prime is 0. And, okay, I is positive. So this tangential, in the sense, this is vertical in the limit. This is vertical, but you have a point where the both touch, but you go through, so you do not stay, let's say, in contact. So because the second derivative is non-zero. And then the proposition says, if you have a generic tangential singularity, then for epsilon small enough, there exists a unique cusp singularity in the vicinity of U0, 0, and it is of class, say, infinite. Well, I would here say infinite epsilon, but I mean smooth inadmissible monomials. Okay, I now go to two theorems, but I need two notions. The first notion is genericity with respect to the divergence integrals. The two-layer slope-fast family, depending just on the two breaking parameters, is said to be generic with respect to the divergence integrals if the following conditions are fulfilled. First of all, your S0 must be a regular curve. No common zero here. Kernel singularities are generic. Tangential singularities are generic. So we keep everything generic. And then the theorem says, consider a two-layer slope-fast family depending just on the two breaking parameters, generic with respect to the divergence integrals. Then the limit critical set is a regular curve. It contains a finite number of singularities of codimension 2, the kernel singularities and the tangential singularities. There is a, say, infinite epsilon family of regular curves. The S0 remains, is stable, bifurcating from S0. And for epsilon strictly positive, S epsilon is the critical set of the map phi epsilon. It contains a finite number of cusp singularities, bifurcating from the active kernel singularities and the tangential singularities. All of the points are fault singularities. In this generic case, that's exactly what you get. And then to end, I will add some more parameters. So instead of just sticking to two breaking parameters, I add more parameters. And we introduce what is called a special finite codimensional slope-fast system. Now we have a certain value of the parameters. Is a two-layer slope-fast system whose slow divergence integrals have the following properties. You always keep the condition guaranteeing that this is regular. Okay. But now you also take care of, you know that S0 at a certain value mu0, it can have these segments from boundary to boundary, it can have closed curves. The closed curve is not important, but the segments are. So you count the number of segments that you have in S0 mu0, C S0 mu0. You require that along S0 mu0 there are just fault singularities, kernel singularities, and tangential singularities, nothing more. At each active kernel singularity, you ask the two simple curves I minus j equals 0 and k minus l equals 0 to have a contact of finite multiplicity. They are no longer transverse, they have finite multiplicity. At each horizontal tangential singularity, you ask the function u to I prime minus k prime to have finite multiplicity. And at each vertical tangential singularity, you ask the function j prime minus l prime to have finite multiplicity. So it's more general, but still very restricted. And then I introduce, for such a special finite codimensional system, let sing mu0 be the set of all active kernel singularities and tangential singularities, so you do not need to look at the mutes, the kernel singularities. The singularity multiplicity is the multiplicity at each singularity m, and the singularity multiplicity of the family is the sum of all these the singularity multiplicities of these points. And then you define the codimension of x epsilon eta 0 as the singularity multiplicity of the system plus the number of segments, right? And the theorem says, let x0 be any unfolding of a special finite codimension, then the cyclicity is bounded by the codimension plus 1. And the proof has been given by the person that spoke before me, because you use Khovansky and you do exactly what you did. You use Khovansky and you can prove this. That's all I wanted to say. Thank you.
Time for questions, comments.
So can you find this kind of two-layer canard transitions when you bifurcate higher order contact points, like cubic contact points between the... I mean, can you localize this phenomenon nearby some higher order type of contact points?
Yeah, probably. Yeah. But you can have it without going close to... I now see that I could have been much slower. It's terrible. No, you can for sure have it when you come close to these points, but you do not need to go that close. Because, for instance, if you look at the study of the Liénard equations, and you would like to treat all possible cases separately, yeah, you cannot avoid to encounter these animals. So, of course, if you stick to classical Liénard, you won't find more. But it's all, if you really want to treat all cases, it's always the program, let's say, how to prove that a certain Hilbert number or a Smale number, how to prove that it is finite. Then you need to look at the individual cases and try to prove that they have a finite cyclicity. But it's not avoidable to encounter these things. So you need to do them.
Some more questions? Okay, then thank you very much.
Este es el tema que hablaste el año pasado. Sí. Tienes más cosas. Me gustan. Sí. Es un tema que me gusta. Es que un día salí a hacer cosas en este esperando que pagues, pero me gustó mucho y ahora más. Puedes reclamar y ser más bueno, ahora no puedes cambiar tampoco ya. Se puede tomar una
Estamos esperando o Marco. Ele não vem? Eu fui perguntar para ele quando estou passando.
Ele fala que é um tipo de
Conferir se ele está na boca. Conversa ali.
Welcome back, everyone. After this lovely celebration, we return to the activities of this lovely meeting. I am very happy to present to you Igor de Jesus from Unicamp. He will talk about construction of partially hyperbolic geodesic flows via conformal deformation.
Thank you so much for the invitation. Thank you for the opportunity to talk here. I hope I can entertain you for 15 minutes. Can you hear me? Yes. Okay. So I'm gonna go straight to the results, and then I will break down every part of it. So if we start with a Riemannian manifold that is locally symmetric, I'm gonna explain what is that. The curvature, sectional curvatures between -1 and -1/4, we can deform this metric in such a way that the geodesic flow is now partially hyperbolic and not a nozzle. The second result is similar, but here we have a better control on the Riemannian sectional curvature that are negative. So with a different deformation, we can obtain that the geodesic flow is partially hyperbolic, not a nozzle. We have a closed, just a single closed geodesic with a parallel Jacobi field along it, and all the sectional curvatures outside these closed geodesics are negative. So for this theorem, we have a lot of consequences for the examples that we constructed. The geodesic flows are partially hyperbolic, non-azimuth, ergodic for the Liouville measure that I'm going to define. They are mixing, expansive, they satisfy the SH property. By SH, I mean that the strong stable foliation has a point for which we have some expansion in the center direction for forward iterates of this point. Okay? And they have unique measure of maximal entropy. So a lot of those properties are just consequences of stronger results that we have for geodesic flows with some properties. Okay? So let's define what is the geodesic flow itself. So if you have your manifold here, M, you pick a point X and a tangent vector V, you're gonna see the geodesic starting from this point here. Let's call it, I don't know, gamma xv at time t. So the geodesic flow takes this vector here and send it to the tangent vector to this geodesic at time t. So this is the geodesic flow applied to V. Okay? So you see that it's a flow that it's not defined on the manifold, but on the tangent bundle of the manifold. Okay? Classical results about geodesic flows is that when the sectional curvature are all negative, then your geodesic flow is of a nozzle type. So it's uniform hyperbolic. And if you have an nozzle geodesic flow, you have some consequences on the geometry of your manifold. So your Riemannian metric has no conjugate points, which I'm going to define later. Okay, so how do we study the geodesic flow in general? So if you remember what is an Anosov diffeomorphism or Anosov flow, it has something to do with the derivative acting on the tangent bundle of your manifold. So here we have a flow defining on the tangent bundle of the manifold, right? So the derivative of the geodesic flow is acting on the tangent bundle of the tangent bundle of a manifold. So we need some way to study this map. So the way we do it, the Riemannian manifold induces a decomposition of the tangent bundle into two subbundles, called horizontal and vertical subbundles. Each of them are isomorphic to the tangent bundle at each point. So here, it's not exactly the sum, but T, so the horizontal at the point X is isomorphic to Tx of M, and the same for the vertical bundle. Then every flow is integrating some vector field. With this decomposition, the geodesic vector field has a very nice decomposition. So it's reading like this. Also, because of this decomposition, we can define a Riemannian metric on the tangent bundle of the manifold that is called the Sasaki metric. So you take every tangent guy here is just a pair of vectors on the manifold. So you just sum the Riemannian metric applied to the correspondent vectors. Okay? So with this Riemannian metric on the tangent bundle, we can define a contact form on the unitangent bundle of the manifold. The unitangent bundle are the vectors tangent to the manifold such that the norm of them is 1. So now you have a compact manifold to work with. So by contact form, I mean that when you take the wet product with the exterior derivative to the power n-1, now this is a volume form on the unitangent bundle, and then it induces a measure that is called the Liouville measure. So every time you hear about the ergodicity of the geodesic flow is referring to the Liouville measure. Maybe if you're explicitly saying for some other measure, it's always the Liouville measure. Okay, now we have a nice description of the derivative of the geodesic flow. So the way it behaves depends on Jacobi fields. So what is a Jacobi field? So if you have a geodesic here, let's say gamma, you can consider a perturbation by geodesics. You can see this as a map that goes from, let's say, some interval times minus epsilon epsilon. So it's a variation for geodesic. So every single curve here is a geodesic. If you fix some parameter here, you have a curve, and then you take the derivative of this curve at this point. So you have a vector field along your geodesic. So this is called the Jacobi field. It also relates the curvature of your Riemannian manifold with these Jacobi fields. So Jacobi fields, you can prove that they satisfy this equation here. So this is the Riemannian curvature tensor. So if we remember from our Riemannian manifold course, if you have constant sectional curvatures, you know that if we start at 0, your Jacobi fields, the size of Jacobi fields grow linearly. So this is for constant curvature equals to 0. For positive curvature, the size of Jacobi fields go like this. And for negative curvature, it grows exponentially fast. So this more or less illustrates why when you have all sectional curvatures negative, then your geodesic flow is of a Nosov type. So you have expansion exponentially fast of the vector fields, of the Jacobi vector fields, and you have contraction to the past for some directions. So what is partially hyperbolic? Usually the definition that people use is that you have a decomposition into invariant bundles such that this guy is uniformly contracting, this guy is uniformly expanding, and the center guy you have some intermediate behavior. You may have some directions where you don't have any expansion or contraction. There is another criterion that is pretty much you have a continuous family of cones. So let's say this is the point X, this is the point, let's say GT of X. You have a constant family, a continuous family of cone fields, such that when you apply the derivative to the vectors inside this cone field, you're sending this to a smaller but longer cone inside the cone that is defined. So this is what we use to prove that it's partially hyperbolic. So where do we start? There is a nice paper by Patrick Eberlein from the 70s, which he states several conditions that are equivalent to have a geodesic flow that is anosov. So the one that we are interested in is that you have no perpendicular Jacobi field tangent to along a unit speed geodesic such that its size is bounded from above for every t. So in particular, these imply that every single geodesic, for a geodesic flow that is anosov, it must cross a region with some negative curvature. Okay, so if you want to break, let's say, the anosov property, we need to find some zero or some positive curvature for every time. So how do we do that? So another way to illustrate that, it's a paper by Ruggiero that states that the C2 interior of the Riemannian manifolds, of the Riemannian matrix for which we don't have conjugate points, coincides with the matrix for each of the geodesic flow is of anosov type. So what we do is pick a very special Riemannian metric inside this class, and then you deform it to produce some guy outside. So the first result, we produce a guy outside this set. The second result, we actually produce a guy on the boundary. So the matrix on the boundary, we don't know much. So the first step to understand this boundary is producing an example and see what properties can we obtain. Okay? So let's go to the deformation. So you start with closed prime geodesic of period t. So by prime, I mean that it doesn't intersect like this, but actually intersect like this. Okay, so it's a proper closed orbit for the geodesic flow in the tangent bundle. So for the Riemannian matrix that we are considering, you can break the tangent bundle into vectors for which you have curvature -1 with the direction of this geodesic, and vectors for which you have curvature -1/4. So you just take the parallel transport along this geodesic, and then you produce a tubular neighborhood along this geodesic. So inside this tubular neighborhood, we are going to change the curvature, the Riemannian metric to change the curvature. So it's a very local deformation of the metric. But so the way we do it is considering a conformal map reading like this. When you write the conformal relation between two metrics like this, you have a very nice relation between the covariant derivative relating both. So if you start with a geodesic for the initial metric, you want to know when this is a geodesic for the new metric. It's sufficient to take some function h such that the gradient of this function is 0 along this geodesic. Then you have a geodesic for the new metric. We also have a very nice relation between the sectional curvatures. And here you can just think that those guys are relating second derivatives of the function h, and here you have some first derivatives of the function h. So if you know some PDE, you can say, okay, I need some conditions, and then I just choose a function h that satisfies this condition, and then we are done. Otherwise, you can analyze the conditions that you need, and then you just write down explicitly the function in coordinates. So if we have this, and all these properties, what we get from this equation is just the initial sectional curvature minus one half of the second derivative in some direction of the function h. So you just choose this function to have a second derivative in such a way you can make this curvature vanish. And then you break the anosov property. So this is just the graph of the function h that we choose. So to prove that it's partially hyperbolic, the contraction of the cone fields is equivalent to evaluate this derivative here and then showing that it's positive. So the way we do is separating cases where the geodesics are parallel to the central geodesic or almost parallel, and then you prove that you can approximate this quantity by this equation here, by this function. Then you prove that along the geodesic it's positive, and then you shrink as much as you need the deformed region in order to have this positive along every point. Okay? So for transversal geodesics, what you have is that they cross this region very fast, and then they spend a lot of time in negative curvature because you're not changing the curvature outside, and then you have contraction of the cone fields again. So by doing this, you prove that you have dominant splitting of this form with same dimension for the strong stable and strong unstable bundles, and then we have a nice lemma that says the vectors in those bundles are contracting for the future and for the past, and then you get partially hyperbolic. For the non-positive case, we just make a different deformation, so we are not multiplying by a conformal factor every direction, but just the direction of the geodesic. So now we have more control on what is happening with the curvature. So you are not screwing a lot of directions of the curvature, of the sectional curvatures, and then we can prove that it's just analyzing this one-dimensional function, and then you have non-positive curvature. As a consequence, we have that this geodesic has, this new metric has no conjugate points. The geodesic flow is expansive because otherwise you would have flat strips on the universal curve. So this is not possible because your curvature is always negative and is zero just along a geodesic. It's ergodic because it's rank 1, and the set of vectors with rank bigger than 1 has measure 0, and then it also has unique measure of maximum entropy by a paper from Knipper that you just apply straight and then you get the results. That's it.
Nice talk. Are there any questions, suggestions, or comments from the audience?
I know the ergodicity for the classical one, and then I didn't quite understand why is it ergodic. Can you explain why, in your case, the partially hyperbolic one?
Essentially, there are a few papers by Baumann, Breen, and Burns, which they prove that if your metric is rank 1, then you have that your geodesic flow is conjugate to a Bernoulli shift. But what is missing in their proof is that if your metric is rank 1, you don't know if the set of vectors with rank bigger than 1 has measure 0 or not. If they have measure 0, then it's ergodic, and this is our case. So you just apply directly their result. So nothing special that we use it here. We just use their result straight.
Any more questions? So we thank the speaker again. Now I have the pleasure to introduce you to the next speaker, Pedro G. Matos from UNICAMP, and he will talk about entropy and non-deterministic chaos for piecewise smooth vector fields.
Thank you. I would like to thank the organizing committee and the scientific committee for having me here, and also congratulate Professor Marco Antonio. This presentation is based on 2 papers. The first is a joint work with Otávio Gomidi and Regis Varão, and the other with Rodrigo Eusébio and also Regis Varão. So I'll start talking about our setting. We're going to talk about piecewise smooth vector fields here. Okay. So the main models I want you to have in mind are the beam model, is this one, and the sphere model. Okay, so I'll explain the beam model now to show how piecewise vector fields work and how we are defining the orbits on our case. So we start with the manifold, and there is this submanifold that's codimensional one. We denote it by sigma. It's called the switching manifold. And it divides our original manifold in two parts, n plus and n minus. And on our manifold, we define on this n minus region, which n minus and n plus are called regular regions. Okay, so on the regular regions, we define smooth vector fields, and they define these smooth flows. But on the switching region, we have to decide how our dynamics is going to work. Okay, so the standard way we do this is to divide the switching manifold in some parts depending on how the orbit flows of the regular regions arrive or leave the switching manifold. Okay, so this part is called a crossing region because there's orbits arriving from one side and leaving from the other side. And also here is a crossing region, but going to the opposite way. And on this part, both flows are arriving, okay? So we call it a sliding region. And on this part, both flows are leaving, and we call it also a sliding region. When they are leaving, this is also called this escaping region or unstable sliding region. And this, because they are both arriving, we call it the stable sliding region. And on the boundary of these regions, we have the tangent region. They are characterized by when at least one of the smooth vector fields is parallel to the switching manifold or is zero. And we're going to use Filipov's convention to define also a flow here on the sliding region, okay? So this is defined using the convex combination of the tangent vectors of each smooth vector field at the sliding region. And this defines a vector field here and also a flow on the sliding region. So the orbits we are going to consider possible solutions of our piecewise smooth vector field are concatenations of regular parts of the orbit, or regular orbits of each smooth field. So here is an example. We can start at this point and we follow the orbit. And when we reach a crossing region, we just go through and concatenate with another regular part. And when we reach the sliding region, we cannot go through. So we have to follow the sliding field. And when we reach this this unstable sliding region or escaping region, we consider that any orbit that is leaving here is going to be a valid orbit. So in this case, we can consider this a valid solution of the system, but also this is another valid solution. And the point is that they both started at the same point, and they're valid solutions, but they're different. So we don't have uniqueness of solution under these definitions, okay? So this is what I mean when I say non-deterministic chaos, right? So what is chaos in our case? Classically, when you have a continuous map on a metric space, the definition by Devaney is that this map is chaotic when it is transitive, has periodic orbits, the periodic orbits are dense, and it's sensitive to initial conditions. And it's also a classical result that transitivity and periodic orbits being dense implies sensitivity to initial conditions. And generally, when we think about chaos, we think at first about sensitivity to initial conditions, right? Some system is chaotic when after some time two orbits are gonna go apart, right? So we're gonna emulate the definitions, but now for our Filipov systems. So we say our Filipov system is topologically transitive when given two open sets, we can start at one and reach the other using a Filipov orbit. And here are the beam and the sphere models I showed before. So why is this transitive? It's easy to see, for instance, in this beam model, every orbit is gonna eventually reach this point P. And each orbit leaving the point P can also eventually reach any open set. So because of the existence of this point P, we can start on any open set and reach any other open set. Okay? And the same happens here because of these points. And how we define sensitivity now? Sensitivity to initial conditions is going to be defined as follows. We start with a delta, positive delta that is fixed. And for each open set U, we can find, if we can find Y and X and Filipov orbits that eventually become delta apart, we say this system is sensitive. Okay. So we define a chaotic Filipov system in the same way. We use this definition of transitivity. We need periodic orbits being dense, and it's sensitive to initial conditions. So our first result here is that in our setting, when we have a Filipov system with non-empty sliding region and in dimension 2, we can show that if the system is transitive, then it is chaotic. So in this case, transitivity is sufficient to have a chaotic system. But one fair question now is this really a good definition of transitivity? It kind of seems that because of the existence of this escaping region, it's very easy for the system to be transitive, right? Because you can leave whenever you want here, so it's easy to reach every open set you have. And the same is true here, okay? So our approach to try and found this definition of transitivity in a more classical definition is to use orbit spaces. So orbit spaces are spaces that are associated to our Filipov system, but they have good properties. You can use them to kind of disentangle the orbits. And this is going to be more clear after I explain. But this means that we can recover uniqueness of solution in this new system. And in this way, we can use the orbit spaces associated to a system to study global properties of the Filipov dynamics. And the motivation for orbit spaces are the study of endomorphisms. This is a tool used in endomorphisms. It's also called orbit spaces, and it's also a space we associate to recover the uniqueness. So this is how we define this abstract M tilde space. Our orbit space is going to be this M tilde space, okay? So we have the base manifold here, where there's the Filipov system. And for each possible maximal orbit here, this is going to be one element of the orbit space. So when we have another orbit, even if this is starting the same point and for a long period they coincide, if in some time they spread apart, they are considered different orbits, and it's going to be represented by a different element of the orbit space, okay? And we can also define a flow in the space. So the space has a dynamics that's related to the dynamics in the Filipov system. The way we do this is, first we have to consider that each orbit has a starting point. So it's not only the image, but really the solution of the system, okay? When we consider the same orbit, but starting at a different point, this is gonna be a different orbit here, a different element. And you can, again, consider another starting point, and this is gonna be another element here. So our flow in the orbit space is gonna be to walk with the starting point along our given orbit gamma 0. And we can do this for every orbit, okay? So here is the more formal definition. Let's say we have this being the set of maximal orbits, and here orbit, I mean Filipov orbit, right? And this is gonna be the flow, okay? You just add here the time of the flow to change the starting point. Besides that, we can also define a distance on this orbit space. So this is also based on the distance of the Filipov space, okay? When we have gamma 0 and gamma 1, we're going to consider the integer times, and we calculate this area, and every area of integer differences, okay? And we sum them all. So we are gonna consider all these areas, but to make sure that this is it's convergent, we have to use a weight. So we define the distance like this. There is a weight, an exponential weight, and here are those areas given by the integral of the distance. It's possible, when we define it this way, it's possible to show that the flow is continuous, and it's also an invertible flow. So the orbit space is, now it's an invertible and continuous dynamics that we have associated to the Filipov dynamics. And we can also show that the orbit space M tilde is separable, bare, and perfect. This is important because when we use classical systems, there is the definition of topological transitivity using open sets, but there's also the definition using dense orbits, the existence of dense orbits. So in our case, they are going to be equivalent. Okay. So we know that these two models are transitive, but the question is, are their orbit space transitive? What's going to be important here is the existence of this point P and these points, these tangent points T2 and T1, okay? So the orbit spaces associated to these systems are going to be transitive. And the general question is transitivity in the orbit space related to transitivity in the Filipov system, and how are they related? So we are able to prove that when we have transitivity above, this implies that the system below is transitive. And under some circumstances, or for a specific class of systems, the converse is also true. So we have proved that this is true when the system above is transitive, the system below is also transitive. And under this hypothesis, it's also true that the converse is also true. And this basically is what I explained before. We have those tangent points, and they are connected between them, and every orbit eventually reach these tangent points. So any system, any Filipov system satisfying this will have the associated orbit space also transitive. So finally, I'll briefly talk about entropy. Entropy is another tool we use to measure chaoticity of a system. And in our case, we use the definition presented first by Antunes, Carvalho, and Varão. we define the topological entropy by the topological entropy of the time one map of the flow in the orbit space. So in the orbit space, we have an invertible and continuous system, and we have a definition of topological entropy. And so we define the entropy in the Filipov system by using this associated system. And again, in our setting of a two-dimensional Filipov system with sliding, we can show that if the system is transitive, the entropy is going to be strictly positive. And the idea is because we can find these different loops returning to a tangent point. So it's going to be, the entropy is going to be greater than log 2 times the constant. So that's it. Thank you.
We have time for one question for the audience, from the audience. So let's thank the speaker. And the last talk of your Thursday, it is an honor for me to present Professor Luis Fernando Melo from Universidade Federal de Itajubá. He will talk about planar current fields.
Thank you for the introduction. I thank the organizers for the invitation. It's a great pleasure to be here in this meeting celebrating the birthday of Professor Marco Antônio Teixeira. My talk is about planar current fields. In fact, my talk is an exercise in the qualitative theory of differential equations and the complex analysis. This is part of a joint work with Denis Braga, Alexander Fonseca, and Ronísio Ribeiro. The plan of this talk is the following: brief introduction, all the results on this subject, some results up to the last workshop, the last year, and more new results. The first part, I will consider the identification of the complex plane with the R2, giving a complex number, Z. I will identify this complex number with this ordered pair. So giving a complex function, f, of this form, this u is the real part of this complex function, v is the imaginary part of this function. There is a usual way to construct a vector field in the plane. And the components of the vector field are just the real and imaginary parts of the complex function. This is done in general. For example, in this article of Professor Gazul, and in this more recent article of Luis Gouveia, Paulo Ricardo, and Gabriel Rondon, for example. Okay? But I will not use of this type of definition. Giving a complex function, I will call it a wave function. U and V are the real and imaginary parts of the wave function. I define the current field in the plane by this way. U gradient of V minus V gradient of U. This is the way I construct the current field. This is a very particular way to construct a vector field in the plane. So in the context of the quantum mechanics, the current field is the probability current. The equilibrium points of this vector field are called phase vortex, or simply vortex. This is the article that we can find physical interpretations and the applications of this context. The title of this article from Michael Berry is Phase Vortex Spirals. This is the first page of the article, and in this context we call the integral curves of the current field flow lines. Okay? By definition, it's easy to see that the vortex of this vector field are in relation with the zeros of the wave function. Where u and v are zero, we have zero, so we have an equilibrium point or a vortex of the current field. So, in fact, without any hypothesis, it's not true that the flow lines circulate a vortex. For example, if you take this wave function, the current field has this expression, so it's easy that the unique equilibrium point of this vector field is the zero of this wave function. So we have an isolated vortex at the origin, but the flow lines do not circulate, do not spiral the vortex. We have this phase privilege. So in this article with Dennis Braga, we put some hypotheses in order that the vortex, the flow lines circulate the vortex. From the qualitative theory of dynamical systems or qualitative theory of differential equations, put conditions in order that the vortex be monodromic. Okay? The simplest one is the following. We take the curve, the zero level of the real part of the wave function, IV, the zero level of the imaginary part, and we put the simplest hypothesis that these two curves are regular and meet transversally at the origin. So we have this hypothesis. With this hypothesis, we have, in fact, the vortex is monodromic, and this hypothesis led us to the center focus problem. And this problem was studied in this previous article here. Okay? So it's worth to mention that in this context, the wave functions studied by Berry are not holomorphic. So now I assume that the wave functions are holomorphic. In this case, by using the Cauchy-Riemann equations, the current field J equals U gradient of V minus V gradient of U can be written as I psi, the derivative, the conjugate of the derivative of the psi. This notation means the vector field is the real part of this function and the imaginary part of this function. Okay? So it's easy to see that the zero, the equilibrium points of this vector field under this hypothesis of holomorphic are the zeros of the wave function, the vortex, and the zeros of the derivative of the wave function. The bar means the conjugate in the complex sense. Is here. So it's easy to prove that if the wave function is holomorphic, then the current field is Hamiltonian. The proof is take the divergence of the current field. If you take the divergence writes in this form, but the real and the imaginary parts of your holomorphic functions are harmonic. So this expression is zero. Okay? So in this setting, the current field is Hamiltonian, and the first integral, the Hamiltonian function, is given by this expression. Okay? The first theorem is the following. Take a wave function, holomorphic wave function, if Z0 is a zero of the current, the wave function, a zero of the order k, then the corresponding point in this plane is a center of the current field. The proof is very easy because if you have a zero of the wave function, this is zero, so you have a local minimum of the Hamiltonian function. If now Z0 is a zero of order k of the derivative of the wave function, but is not a zero of the wave function, the corresponding point in the plane is an equilibrium point of the current field with 2 times k plus 1 hyperbolic sectors. The proof is very easy. Write the current field under this hypothesis, perform blow-ups, and in the blow-ups, I will have only settle in a certain number such that we have this quantity of hyperbolic sectors. Okay? It's not important here. For example, consider this wave function, a holomorphic function. So the zero of this wave function is z equal to 0. The derivative here, the zero of the derivative is z equal minus 1. So we have a center corresponding to the zero of the wave function at the origin, and I have the order of the zero of the derivative of the wave function is 1. So we have 4 hyperbolic sectors. We have a saddle at this point. This is the local phase portrait of the current field. Now you have the domain is the whole complex C, and I have a polynomial. The wave function is polynomial non-constant function. Okay, so in this case, The current field has a finite number of equilibria. The proof is trivial because polynomials of any degree has a finite number of zeros, and the derivative of polynomials are polynomials, and they have a finite number of zeros. Every orbit of the current field is bounded. This is also trivial because this function is proper, so each level set is a compact, so all the orbits are bounded. The equilibria corresponding to the derivative of the wave function belong to the convex rule of the set of equilibria corresponding to the roots of the wave function. Have center, 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 for example, for roots, and here we have the equilibria corresponding to the zeros of the derivative of wave function. This is a consequence of the Gauss-Lucas theorem. All the zeros of the derivative of a polynomial are in the convex rule of the zeros of the polynomial. If we compactify, take the Poincaré compactification of the current field will be polynomial, so you can take the Poincaré compactification. If you take the polynomial of degree n, the corresponding current field has degree 2n minus 1. If we take the equilibrias of this Poincaré compactification, the compactification does not have equilibria at an infinity, so the infinity is S1, the boundary of the Poincaré disk, is a period orbit of the Poincaré compactification. And this is an interesting statement. The current field has a global center if and only if, in this class, the wave function is obviously polynomial, but writing in this form. Okay? The idea is very easy. For one implication, if the polynomial has this form, it's easy to see that we have a center at Z0, but this center is not only local but global. And if the current field has a global center, it in particular has a local center, so it's a zero of the wave function. There are no other equilibrium points, so the wave function has this form. For example, consider this polynomial wave function, which is the zeros of this wave function are the roots of units. So you have simple zeros. Each one corresponds to a center of the current field in these points. The derivative of this function has a zero at 0 of order 3. So we have 2 times k plus 1 hyperbolic sector. K is 3, so we have 8 hyperbolic sectors in a neighborhood of these equilibrium points. Okay? So this is the phase portrait of the current field. This is other example. We have a polynomial of degree 4. This wave function has 4 simple roots. Each one is a center of the current field. derivative of the wave function has 3 simple roots also. So each one corresponds to a saddle point of the current field, and the phase portrait, the global phase portrait is this one. We have 4 centers, and we have 3 saddles in the convex hull of this quadrilateral. And we have the unbounded period annus here. All the orbits are bounded in this case. Okay? Some new results. Item 5 of Theorem 2 is this one. In the case of a wave function is a polynomial, the current field has a global center if only if the wave function has this one. I will generalize this result taking an entire function. Assume that the wave function is a holomorphic function in the whole C. That is an entire function. The corresponding current field has a global center at a point if and only if this entire function is polynomial. Okay? Wow, the idea of the proof is the following. One implication is trivial. If this entire function has this form, obviously, I have a global center from item E. If you take here, this function is decreasing. Okay? But this implies a contradiction by using the Picard-Gray theorem. The Picard-Gray theorem says that if I have an essential singularity here at the origin, any punctual neighborhood of this essential singularity, the image is all the complex plane except at most one point. So it's not possible to have this function strictly decreasing. Okay? This is a contradiction. This contradiction appears assuming that we have an essential singularity at infinity. So in fact, we have a pole at the infinity. So the wave function is a polynomial wave function. And the proof follows from the previous theorem. This is the idea. For meromorphic function, now, this usual way to define meromorphic function is holomorphic in the set, except for a set of isolated points, the poles of the function. If this meromorphic function is rational, of this form, P and Q are polynomial complex functions, we define this number n of the wave function, the difference of the degrees of P and Q. Okay? So n is the difference of this degree. Degree P minus degree of Q. So the idea now is to study the phase portrait of the current field on punctual neighborhoods of the singular points associated with the poles of the wave function. We have this theorem. The wave function is a meromorphic function defined on D, and J is the associated current field of this meromorphic function. So this function phi 1 over the original wave function is also meromorphic on this set, and the two current fields are topologically equivalent. In fact, this function, the vector field defined by this function. This current field is Hamiltonian with the same first integral, the same Hamiltonian function as psi. Okay? The singular point Z0 is a center of the current field of this meromorphic function if and only if this point is a pole of the order k of the wave function. The idea is to take this item 1, so this pole is now a 0 of the new wave function. If for a 0 of the wave function, we use the first theorem. The zeros are in correspondence with the centers. Okay? Now, if I take the domain of the meromorphic function equals C, every orbit of the current field is bounded if and only if this meromorphic function is a rational function, but with this number different from 0. Okay? It can be proved that if this number is 0, the current field has always an unbounded orbit. So it's not satisfied. Okay? Again, if we take the domain of this meromorphic function, C, and Z0 is a pole of this meromorphic function, the current field has a global center at this point if and only if this meromorphic function is a rational function defined by this way. The degree aqui is exactly the order of the pole. Okay? The proof of this theorem follows from the previous theorem and item 1 that is trivial. Okay? In the last part, consider a kind of wave functions with essential singularities. For example, define this function. We have this function and belongs to this set, 0, 1, and phi is any meromorphic function. So it's a very particular way to consider a wave function with an essential singularity. Any pole of this meromorphic function is an essential singularity of the wave function psi. If Z0 is an essential singularity of psi, that is, Z0 is a pole of the function phi, then the local phase portrait of the current field on a punctured neighborhood of Z0 has 2k elliptical sectors, where k is the multiplicity of the pole Z0. The proof of this theorem is take this wave function, write the current field, take the blow-ups. Now, instead of saddles at the exceptional divisor, we have nodes. We have nodes. So here we have elliptic sectors. Okay? The proof is very easy, but it's also taking a lot of problems. An example to finish, consider this wave function. This wave function is this type, taking m equals to 0, and the meromorphic function 1 over z to the power 3. Okay? So here, m is 0, the meromorphic function is rational. Z0 at the origin is a pole of order 3 of this meromorphic function. So, by the last theorem, we have 2 times 3 elliptical sectors on a punctual neighborhood of the origin. Okay? So the phase product is here. 6 elliptical sectors on a punctual neighborhood of the. This point is the essential singularity of the wave function. Okay? We don't have any other results about the essential singularity, only for this kind of wave functions. Okay? So, again, Professor Marco Antônio Teixeira, congratulations for your birthday. Thank you very much for your attention. These are the sponsors of this talk. Thank you.
Thank you, Professor Luis, for your nice talk. Are there any questions from the audience? Any comments, suggestions?
Just a question. Maybe I didn't understand well. In the theorem 4, the first point you said, the function phi and its reciprocal are topologically equivalent, but the number of zeros is not the same for one function and the other, I think.
No, the zeros are not the same, but the zeros of psi are poles of the phi and the reciprocal. So if I have a pole of this function, will be a zero of the psi, of phi. And the zero of phi, I have the previous theorem.
Thank you. Thank you.
Any other question? So let's thank Professor. Before we call it a day, Professor Douglas would like to make some announcements.
Okay, so thank you very much for all the speakers today and for the audience. In the first day, I told you